Hello. In the previous lecture, we started with an algebraic extension and then considered all the elements alpha in E in the larger field, such that the minimal polynomial of alpha over f is a separable polynomial in f bracket x. We call this set E sub sep, and we showed that E sub sep is indeed a field. It is an intermediate subfield of E over f, and by definition, E sub sep over f is a separable extension. In fact, again, by looking at the definition, we see that if K is an intermediate subfield and K over f is separable, then all the elements of K are going to have separable minimal polynomials, and therefore K would be a subset, a subfield of E sub sep. So E sub sep is the largest intermediate subfield of E over f, which is separable over f. So in particular, if the characteristic is 0, then we know every polynomial is separable, and therefore we deduce that E sub sep is the entire field. This is the case if and only if E over f is a separable extension. So E sub sep equals to E precisely when E over f is a separable extension. And in characteristic 0, we have discussed that every algebraic extension is separable. Now, what happens if characteristic is P is a positive prime? I mean, it's a prime number. It's a positive number. In that case, we showed that every element of alpha, every element of E, to some raised to some power of P ends up being inside E sub sep. Alternatively, we can say the multiplicative group of E over the multiplicative group of E sub sep is a P group. So every element has an exponent that's a power of P. So order of every element in this quotient is a power of P. So this is what we showed in the previous lecture. But the last item brings us to the definition of purely inseparable extensions. So what is purely inseparable extension? So we call E over F an algebraic extension. We call it a purely inseparable extension if one of or all of the following statements hold. So in the next proposition, we show that three properties of a field extension are equivalent, and whenever one of them holds, we say E over F is a purely inseparable extension. So what is the statement? So assume that E over F is an algebraic extension, and characteristic of the base field, and therefore characteristics of both of these fields, is a prime number P. Then the following statements are going to be equivalent. So the first thing is that if I tell you alpha is some number, that's some element that's not inside the base field F, then for sure the minimal polynomial is not a separable polynomial in F bracket X. Alternatively, I can say that E sub sep, this largest intermediate subfield that is separable over F, is just F. You cannot make it larger. So that's the first condition. The second condition is that when I look at the multiplicative group of E and mod it out by the multiplicative group of F, so these are groups, I'm thinking about them as multiplicative groups, then this quotient is P torsion. That means for every alpha inside the larger field, so if it's 0, then there is no content in the statement anyway, because 0 to raise to any power is 0, so it's definitely inside F. If alpha is not 0, then I can think about the coset of alpha in this quotient. And because it's P torsion, that's the same as saying that alpha raised to some power of P is going to be inside F. It's going to be identity, and therefore that means it's going to be inside F for some non-negative integer K. So that's the second statement. That's equivalent to saying that E subset is F. And the last one gives us a description of minimal polynomials of elements of E over F. For every alpha inside the larger field, the minimal polynomial of alpha over F is of the form x raised to some power of p to the k raised to some power of p minus an element of the base field A. So for every alpha, the minimal polynomial is of the form x raised to power p to the k for some non-negative integer k and some a inside the base field. So these three statements are equivalent, and if one of them holds, we say that E over F is a purely inseparable extension. Okay, so let's see why this is the case. Let's go from 1 to 2. So what was the statement of the first proposition? I mean, what was the first statement? It says that every element of E that's not inside F it has a non-separable minimal polynomial. Okay, so the minimal polynomial of every alpha that's not inside E is going to be not separable in F bracket X. So for every alpha, there is a non-negative integer. So this is the assumption that we have. I mean, this is what we have proved in the previous lecture, and I have stated this over here as well, that for every alpha inside E, I can raise alpha to some power of p and end up being inside E subset. And remember the assumption, the first statement, I can alternatively say that is the same as saying that E subset is F. Now, but what we proved, we know that for every alpha inside E, I can raise alpha to some power of p and end up being inside E subset. But E subset is F. And that means what? That means exactly what we wanted to show. So we end up getting that for every alpha inside E, alpha raised to some power of p is inside F. Okay, so that we have. Now let's go from 2 to 3. That means I want to understand minimal polynomials of elements of E. I start with some element of E. By assumption, I can raise alpha to some power of p and end up being inside F. So let's say k is such an element. In fact, what I will do, I'm going to look at smallest such k. So suppose k is the smallest non-negative integer with this property that when I raise alpha to the power of p to the k, I end up being inside F. And let's denote this particular power of alpha by a. So a is an element of F. In particular, that means alpha is a zero of the polynomial x raised to power p to the k minus a. I want to show that this is the minimal polynomial of alpha over F, which finishes the proof. I mean, the proof of this part, that 2 implies 3. So this is a polynomial in F bracket X, and alpha is a zero of this polynomial. Therefore, the minimal polynomial should divide this polynomial. So the minimal polynomial of alpha over F divides x raised to power p to the k minus a. And this division happens in the ring F bracket X, in the ring of polynomials with coefficients inside F. Now, because characteristic of E is p, I have the property that a plus b raised to power p is a to power p plus b to power p. Alternatively, I can say that the Frobenius map is indeed a ring homomorphism. And that means x raised to power p to the k minus a is, okay, so a is by definition alpha raised to power p to the k. And now I can use the fact that Frobenius map is a ring homomorphism and take out the power of p. And that means I can think about it as x minus alpha raised to power p to the k. So this means over E, the binomial x to power p to the k minus a has only one irreducible factor, and that is x minus alpha. Therefore, every divisor of this binomial should be of the form x minus alpha raised to power m for some non-negative integer m. Okay, up to a unit. But the minimal binomial, okay, so if I combine these two observations, I deduce that the minimal binomial should be a power of x minus alpha raised to power m up to a unit, but after comparing the leading coefficients, I should get the equality for some positive integer m. Now I focus on the constant terms of both sides. The constant term of the minimal binomial over f is, by definition, inside f, because the minimal binomial of alpha over f is a binomial in f bracket x. That means all the coefficients belong to f. Now, by looking at the coefficients, the constant term of the right-hand side of this equation, we deduce that alpha raised to power m should be inside f. Okay, so I want to work with the multiplicative group, as the statement that we had was about multiplicative groups. I mean, the assumption, the statement 2 is about multiplicative groups. That's an indication that it's better to think about multiplicative group. So that's why I'm going to separate two cases. If alpha is 0, then automatically the minimal binomial of alpha over f is just x, and we are done. It is exactly of the form that we are looking for, meaning x raised to some power of p minus some constant. The power of p here is just 0, and the constant is also 0. So in this case, there is nothing to prove. From this point on, I'm going to assume that alpha is not 0. That means alpha is an element of the group of units of of E. And now I'm going to look at the order of the coset alpha f cross in the group E cross over F cross. The order of this element, we know that when I raise this element to two different powers, it's going to be 1. It's going to be 1 inside this group, meaning alpha raised to two different powers, so far we know, belong to F cross. One of them is p to the k, and the other one is m. Let's start with p to the k. Because alpha to power p to the k belongs to F cross, that means the order of this coset should divide p to the k, which means order of this coset is some power of p, where the power of p is at most k. So the order of this coset is p to the l for some integer in the range from 0 to k. But remember, we have chosen k in a way that it is the smallest non-negative integer, such that alpha raised to power p to the k is inside f. Now, if I tell you alpha raised to power p to the l is also inside f, and l is in the range from 0 to k, we deduce that l is k. So because k was chosen to be the smallest one, we deduce that l is k, which means that the multiplicative order of this coset is p to the k. Now let's go back to the other, to this star, the relation between alpha and the minimal binomial of alpha. So with this star, we know that alpha, the coset of alpha, the coset represented by alpha raised to power m is also identity. which means the multiplicative order of this element, the order of this element, should divide m, which means p to the k is a divisor of m. But on the other hand, remember here, this m that we have, I mean, the minimal polynomial is supposed to divide, the minimal polynomial of alpha is supposed to divide x minus alpha raised to power p to the k. From here, we deduce that the minimal polynomial is of the form x minus alpha raised to power m, not only for every m should be at most p to the k. So m is an integer, which is at most p to the k, but now we deduce that p to the k should divide m as well. So m is in this range, and it is a multiple of p to the k, so we get equality. So m is p to the k. Now that I know this, I go back to my minimal polynomial. By assumption, m is p to the k, so my minimal polynomial is x minus alpha raised to power p to the k, and that is precisely x to power p to the k minus a, as the Frobenius map is a ring homomorphism. Okay, so this implies that, I mean, this shows that 2 implies 3. Now let's see why 3 implies 1. So the assumption is that the minimal polynomial of every element is of the form x to power some power of p minus an element inside f. Now let's start with some element that's not inside f. So after all, we want to show that E sub sep is precisely f, which is equivalent to saying that every element outside of f has the minimal polynomial of every element outside of f is not separable. So I start with an element outside of f. That's equivalent to saying that the minimal polynomial of such an element should have a degree at least 2. If the degree of the minimal polynomial is 1, that's equivalent to saying that that element belongs to the base field. Now, because alpha does not belong to the base field, the degree of the minimal polynomial of alpha should be at least 2. But at the same time, by our assumption, the minimal polynomial of alpha over f is of the form x raised to some power of p minus an element inside f. Now, this power of p cannot be 1 because alpha does not belong to the base field, which means the p to the n cannot be 1 because alpha does not belong to the base field, which is equivalent to saying that the power of p should be a positive integer. So the power of x, I mean, the degree of the minimal polynomial in this case is divisible by p. Now, if I look at the derivative of the minimal polynomial, I end up getting that it is p to the n times x to power p to the n minus 1. But p to the n is divisible by p and characteristic as p. We deduce that the derivative of the minimal polynomial is 0. And for an irreducible polynomial, this is the case if and only if the irreducible polynomial is not separable, has multiple zeros, and therefore it's separable. So that implies that the minimal polynomial of alpha over f is not separable as soon as alpha does not belong to the base field, which completes the proof. So now we have a better picture of algebraic field extensions from separability point of view. Any algebraic field extension that I give you, you can think about E sub sep, and we get that E over E sub sep is purely inseparable. The top portion is purely inseparable, and the bottom portion is separable. And from here, we can also see that, I mean, from the definition, as I mentioned it earlier, but now I want to summarize it, that if K is an intermediate subfield and K over F is separable, then K is a subset of E sub sep. So E sub sep is the largest intermediate subfield of E over F, which is separable over the base field. So it's equivalent to saying, or it is the definition of E sub sep, that alpha belongs to this precisely when the minimal polynomial of alpha is separable in f bracket x. Sometimes we say that alpha is separable over f. So when we say alpha is separable over f, that's equivalent to saying that the minimal polynomial of alpha is separable in f bracket x. That's the definition of saying that an element is separable over f. Okay, so again, this means that we have this kind of diagram. Whenever I give you an algebraic extension E over f, I can find some intermediate subfield such that the bottom portion this time is separable and the top portion is purely inseparable. So you see the difference between separability criterion and normal criterion. So in the normal criterion, the top portion was the easy one. In the separability criterion, we will see that the both portions will be kind of involved. So what do I mean by that? So we are going to use this theorem in order to understand tower of separable extensions. So again, let me repeat this. Properties of field extensions have this tendency to stay at the surface. So what do I mean by that? So this means that most of the properties of field extensions, if I know it for E over F, then I know for E over K, where K is an arbitrary intermediate subfield. I mean, this is not a fact. This is rule of thumb. Rule of thumb. Now, if my property is defined in a way that you can get it for the bottom portion, then you are in luck. Then that means that most likely there is an if and only if statement hidden there that says that this property holds for E over F if and only if it holds for E over K and K over F for every intermediate subfield K. We have seen this phenomena for the concept of being algebraic. So we showed that E over F is algebraic if and only if E over K and K over F are algebraic for every intermediate subfield. We have seen this for finite extensions. So E over F is a finite extension if and only if E over K and K over F are finite extensions. This is not the case for normal extensions. So E over F can be normal. If E over F is normal, then E over every intermediate subfield is normal. But an intermediate subfield is not necessarily normal over the base field. In fact, the Galva correspondence tells us that the intermediate subfield over the base field of a Galva extension is a normal extension precisely when the K-linear maps, the K-linear automorphisms of the top of the tower is a normal subgroup of F linear automorphisms of the top of the tower. So you see, there is a connection between being a normal subgroup and being a normal extension over the base field. And the same, of course, is I mean the failure. We've also discussed that if for some intermediate subfield K, both E over K and K over F are normal extensions, one cannot necessarily deduce that E over F is a normal extension. Essentially by arguing that if degree of a field extension is 2, then it is definitely a normal extension. Now we created a degree 4 extension, which is not normal, and then found an intermediate subfield that has degree 2 in both of them. So both of these steps of this tower are normal extensions, but the entire extension, the top one over the bottom one, is not a normal extension. So you see that in certain properties that naturally gives us the bottom portion, we can get this if and only if statement. Otherwise, we cannot. Let's see how we can show this property for separable extensions. That's our next goal. We want to show that E over F, an algebraic extension E over F, is separable if and only if E over K and K over F are separable for an arbitrary intermediate subfield K. Okay, so let's see how we can do that. So this is our goal. Given an algebraic extension and some intermediate subfield, you want to show that E over F is separable if and only if E over K and K over F are separable. Surprisingly, in this case, the bottom portion will be easier, and that's why we do have this statement. Okay, but let's go about it. I start from left to right, and then I have to show that both E over K and K over F are separable extensions. Let's start with harder one, E over K this time. So I start with some element of E. Here it should be E. So I start with an element of E. I look at its minimal binomial over F. By assumption, because I'm told that E over F is a separable extension, we do know that the minimal binomial of alpha over F is separable in F bracket X. Now I want to show that E over K is separable. This means I need to think about the minimal binomial of alpha over K. This type of argument we've seen before when we wanted to show a primitive element theorem based on the finiteness of intermediate subfields. So there we argued that when I extend my base field, the minimal binomial should divide the minimal binomial of the previous field that we chose. What do I mean by that? So the minimal binomial of alpha over F is of course a binomial with coefficients inside the larger field K. And alpha is a zero of this binomial. And so the minimal binomial of alpha over the larger field should divide the minimal binomial of alpha over F. Okay, so what? We do know here that the minimal binomial of alpha is separable in F bracket X, and it is also irreducible. That means this polynomial does not have multiple zeros when I can split it completely into linear factors. It does not have a repeated factor. It does not have multiple zeros in its splitting field. Now, this means every divisor of this polynomial should have the same property. It's not when I factor m sub alpha into linear factors, I'm not going to have repetition. So any divisor of this polynomial is going to have the same property. In particular, the minimal binomial of alpha over K is going to have no multiple zeros in its splitting field, which is equivalent to saying that it is separable in K bracket X. So altogether, we deduce that E over K is a separable extension. Now you see that the bottom portion is actually rather immediate. If I give you alpha inside K, it is also inside E, and therefore the minimal binomial of alpha over F is separable in F bracket X, as E over F is a separable extension. So that immediately implies that K over F is separable. Okay, so we see that the bottom portion is rather immediate. The same was true for algebraic extensions. When I tell you that alpha inside E is algebraic over F. Of course, when I restrict it to a smaller field, it doesn't change. It's going to be algebraic again. So again, the bottom portion was clear in algebraic case, so we could show the similar tower phenomena property for algebraic extensions. The same was true for finite extensions. The same is true for separable extensions. Okay, so now let's go from right to left. This time the assumption is that E over K and K over F, both of them are separable, and we want to show that E over F is separable. As we have discussed, E over F is a separable extension if and only if E sub sep is equal to E. E sub sep, after all, is the largest intermediate subfield of E over F, which is separable over the base field. Let's also point out that if characteristic is 0, we have already discussed that every algebraic extension is already separable. So if characteristic is 0, there is nothing to prove. From this point on, I am going to assume that my characteristic is a prime number P. Okay, let's go back to E sub sep. I want to show that E sub sep is E. But what do we know? What are my assumptions? I'm given an intermediate field K, and I'm told that K over F and E over K, both of them are separable. But because K over F is separable and E sub sep is the largest intermediate subfield that is separable over the base field, we deduce that K is a subfield of E sub sep. Okay, what else do we know about E sub sep and K? We also know that E over K is separable. What is my next goal? My next goal is to show that every element of E belongs to E sub sep, and therefore E sub sep equals to E. I'm going to use these two facts, that E over K and E over E sub sep. So I'm going to use the fact that E over K is separable and E over E sub sep is purely inseparable, and K is a subfield of E sub sep, in order to deduce that minimal polynomial of every element of E is of degree 1, which implies that every element of E is inside E sub sep. So here when I say minimal polynomial of every element of E, I mean every minimal polynomial of every element of E over E sub sep. That's my goal. My goal is to show that minimal polynomial of every element of E over E sub sep is of degree 1, which finishes the proof. Okay, let's start with alpha inside E, and my goal is to show that alpha belongs to E sub sep. What do I know about alpha? I know two things. The minimal polynomial of alpha over K is separable, and minimal polynomial of alpha over E sub sep is of the form alpha raised to power, x raised to power p to the k minus some element of E sub sep. So because E over E sub sep is purely inseparable, I have two kind of contradictory properties for the minimal polynomials. At one hand, I know that the minimal polynomial of alpha over k is separable, which means it does not have multiple zeros. On the other hand, the minimal polynomial of alpha over E sub sep kind of has only one zero. So it is of the form x raised to power p to the k minus an element of E sub sep. Now let's see how these seemingly contradictory properties get connected to each other. So again, E over K is separable, therefore this minimal polynomial, the minimal polynomial of alpha over K is separable. And that means that this does not have multiple zeros in its splitting field. On the other hand, K is a subfield of E sub sep. So by the similar argument as we have seen before, the minimal polynomial of alpha in this larger field should divide the minimal polynomial of alpha over k. And therefore, the minimal polynomial of alpha over k, the minimal polynomial of alpha over e sub sep does not have multiple zeros, because the minimal polynomial of alpha over k did not have multiple zeros. So we are saying that alpha over e sub sep is separable. But as we have discussed, this is a purely inseparable extension, and the only elements in a purely inseparable extension that are separable over here, that are separable, are in the base field. Okay, let's go over this part of the argument and make sure that we understand it. Because this extension is purely inseparable, the minimal polynomial of alpha over this purely inseparable extension is of the form x raised to power p to the k minus some element of this e sub sep. Now, because I'm told that the minimal polynomial does not have multiple zeros in its splitting field over here, because we argued and we deduced this, and this is an irreducible polynomial, that's equivalent to saying that the derivative of this minimal polynomial should not be 0. Now, if k is not 0, if this power over here is not 0, and the power is not 1, then it's a multiple of p, in which case the derivative of this polynomial is automatically 0, which is a contradiction. Therefore, k should be 0, which means the degree of the minimal polynomial is 1. But a was an element of e sub sep, and alpha is a 0 of this, which means alpha is a. So we show that every element of e belongs to e sub sep. And that finishes the proof. That shows that e is e sub sep, which means that e over f is separable. So we showed this nice phenomena that when I give you a tower, an algebraic extension e over f, then for every intermediate subfield k, e over f is separable if and only if e over k and k over f are separable. So if I give you a tower of separable extensions, the top part of the tower over the base of the tower is going to be a separable extension as well. Okay, so now that we have a better understanding of separable extensions, let's go back to what we started the whole course or the whole journey. We started with zeros of binomials, and we have said that Khwarazmi, Khayyam, Del Ferro, Ferraro, these guys provided equations, formulas for zeros of binomials of degree at most 4. Then people were wondering if there is such a formula for binomials of degree 5 and larger. This was one of the motivations of Galva for creating this theory and understanding that he should focus on the symmetries of zeros of binomials. I mean, what he had developed turned out to be much more important than this particular question. But nevertheless, this was one of his main motivations. So that's what we are going to focus on next in this course. Going back to the history, Abel, in fact, prior to Galva's work, showed that there is no general formula in terms of the coefficients that can describe zeros of binomials of an arbitrary binomial of degree 5, let's say. So what does that mean? There is no formula, there is no function f of a sub 0 dot a sub 4 where a sub i's are coefficients of a binomial of degree 5, and this formula should be involved only with plus, minus, multiplication, division, and taking roots. There is no such formula that ends up being 0 of a polynomial of degree 5 of this form. This is what Abel showed. And Galva went further and showed that by looking at the symmetries of the zeros of the splitting field of this polynomial, we can understand exactly when this polynomial can be solved using radicals, addition, multiplication, subtraction, and division. Okay, let's start the proof. And start the argument, the journey, understand the terms, and so on. Let's start by understanding what it means for a polynomial to be solvable by radicals. So this means that so I give you a polynomial f, and I ask myself, can I describe all the zeros of this polynomial in terms of addition, multiplication, division, and radicals? This means what? So addition, multiplication, subtraction, all of them happen in the field that contains the coefficients of my polynomial. Now I take some radical, and then I again use addition, multiplication, division, and subtraction, which means I look at the field that contains this particular radical, and then I continue like that. So after finitely many steps, I might end up getting all the zeros of my polynomial. So that's going to be our definition of saying a polynomial is solvable by radicals. So again, let's try to understand the definition. I say a polynomial f with coefficients inside the field capital F is solvable by radicals if I can find a chain of fields. The first one is my base field, the next one, and so on, with the following properties. First of all, each time I'm adding some root of elements of the previous, of some element of the previous field. So instead of saying the n sub ith root, I'm saying that when I take alpha I and raise it to power n sub I, it's an element of f sub I. Okay, so I'm adding some n sub ith root of the previous field to get larger field. So again, alpha I can be viewed as the n sub ith root of some element of the previous field. And why am I doing these extension by extending radicals and so on? Because I want to get all the zeros, I want to capture all the zeros of f, or alternatively, I can say that I want to write f as a product of degree 1 factors in my final field extension. So alternatively, I can look at all the zeros of f and look at the field generated by f and all those zeros and get a splitting field of the polynomial f. So this is alternatively is the same as saying that f sub m, my final field, contains a copy of a splitting field of f, the polynomial f, over the base field capital F, or f sub m contains all the zeros of f. Okay, so that's the definition of a polynomial being solvable by radicals. Because of this, we call such a field extension a radical extension. So if I have this chain of fields, we say that f sub m over f is a radical extension. So this means the way that we are trying to understand we are trying to understand if polynomials are solvable by radicals or not. It is related to understanding radical extensions of the base field capital F. So we need to understand what are the properties of radical extensions. Okay, but let's go back to the building blocks of this chain, of this tower of fields. The building blocks are of this form. I'm adding nth root of an element of some field to itself, and these are the building blocks. So maybe it was better to, if I put an I here, then you get a better picture, I over here. But I don't want, because now at this point I want to focus on only one single block. And every single block looks like this, as you can see, where alpha I is the nth root of some element, n sub ith root. There I have an index. Now I want to remove the index and only work with a single block. But we have already seen such a field extension, at least when F contains n distinct nth roots of unity. In that case, we had studied this field extension. In fact, Kummer studied this field extension in relation with Fermat's last conjecture. That's why we call such an extension a Kummer extension. So, but when I say Kummer extension, again, he had already observed the importance of having nth roots of unity inside the base field. So when we say Kummer extension, we have already included these roots of unity to the base field. So we say this is a Kummer extension if F contains n distinct nth roots of unity. Let me quickly go over the statement that you have already seen, but let me also introduce some new mechanism to prove an old result that you've seen in your homework assignments and so on. Suppose that there exists some element inside the base field that has multiplicative order n, and let's call that element zeta. And let's denote a solution of the polynomial x to the n minus a by the nth radical of a. So this notation means a solution of x to the n minus a. So there are n choices. I'm picking one of them and I'm denoting that element by the nth root of a. This choice is not canonical. I'm picking one of them. In that case, the field extension f bracket root n over f is a Galva extension. The group of automorphisms of this Galva extension can be embedded into a cyclic group of order n, and I'm picking this particular cyclic group of order n, the cyclic group that's generated by this zeta, this multiplicative group, generated by this zeta that has order n, multiplicative group order n. And the map I'm going to denote by f sub a, what is it? When I feed it an automorphism, I apply theta to the nth root of a, and then whatever I get, I'm going to divide it by the nth root of a. So that's going to be my f sub a theta. So alternatively, so theta of the nth root of a is this scalar times nth roots of a. Now, claim is that this f sub a is a group homomorphism. and it is injective. So it's an injective group homomorphism. In particular, the domain can be embedded into a cyclic group of order n, which means it is a cyclic group. So the group of automorphisms of this field extension is a cyclic group. Again, these results you have seen before, but let's go over the argument. Because the order of zeta is n, the elements 1, zeta, zeta to power 2, and so on till zeta to power n minus 1, all of these are pairwise distinct. We also notice that every such element raised to power n is going to be 1 because zeta to power n is 1. So altogether, that implies that when I multiply the nth root of a by these powers of zeta, I get distinct elements, and all of them raised to power n are going to give me a. So all these elements, all these distinct elements are zeros of x to the n minus a in this larger field. And of course, this larger field is generated by these zeros because the nth root of a is one of those zeros, which means that this larger field is a splitting field of the polynomial x to the n minus a. And at the same time, it implies that x to the n minus a is a separable polynomial because all the zeros of this polynomial that are listed over here are distinct. So therefore, x to the n minus a is a separable polynomial, which means f joined with the nth root of a is a splitting field of a separable polynomial. That's one of the equivalent properties, equivalent statements that imply that my extension is a finite Galva extension. So altogether, we deduce that this guy is a finite Galva extension. Now, every theta that I give you in an automorphisms of a field extension E over f permutes zeros of a polynomial with coefficients inside f. So if I tell you that E over f is an algebraic extension, and I tell you theta is an automorphism of this field extension, then theta permutes zeros of a polynomial with coefficients inside f. In particular, theta permutes zeros of x to the n minus a. That means theta of the nth root of a should be one of the elements listed over here, some power of zeta times the nth roots of a. So that means theta of the nth root of a is of the form some power of zeta that depends on theta, of course, times the nth root of a. So f sub a of theta equals to, by definition, this ratio, this fraction. It is equal to zeta raised to power I of theta. It does belong to the group generated by zeta. So f sub a is a well-defined function. Now, why is this a group homomorphism? So when I take theta 1 and theta 2, two automorphisms, theta 1 of theta 2 of the nth root of a is what? Theta sub 2 of the nth root of a is this power of zeta times the nth root of a. But powers of zeta belong to the base field. That was our assumption. And theta 1 is f linear. So I can take out this scalar. I get that it's f sub a of theta 2 times theta 1 of the nth root of a. Theta 1 of the nth root of a is f sub a of theta 1 times the nth root of a. Okay, so I had this scalar outside anyway. So altogether we get, you see, this is my new scalar. This is going to be f sub a of the composite of theta 1 and theta 2 then. So f sub a of the composite is the product of f sub a of theta 1 and f sub a of theta 2, which means f sub a is a group homomorphism. Okay, so far we showed that f sub a is a well-defined group homomorphism. The last thing that we need to check is that f sub a is injective. We notice that an element theta of this automorphisms of this field extension, every theta is uniquely determined by its value at f and the nth root of a. But over f we understand, because theta restricted to f is identity. So every such theta is uniquely determined by its value at the nth root of a. As soon as I know what theta of the nth root of a is, I understand it completely. F sub a theta tells me what theta is at the nth root of a. As we can see over here, or explicitly wrote it over here, that theta of the nth root of a is f sub a of theta times the nth root of a. So as soon as I tell you what f sub a of theta is, I'm telling you what theta of the nth root of a is. And that means I'm telling you what theta is. Altogether, we deduce that f sub a of theta gives us a unique theta, which means f sub a is injective. Now I have embedded the domain into a cyclic group, and therefore the domain is a cyclic group, because subgroups of cyclic groups are cyclic. So this completes the proof of this theorem. So altogether, we deduce that every Kummer extension is Galois, and its group of automorphisms is a cyclic group. Okay, so let's go back to polynomials that are solvable by radicals. If I tell you f, polynomial f, is solvable by radicals, that means I'm giving you this chain of fields. Each one of them is created by adding n sub ith root of the previous one to the base field. If I knew that my base field f has enough roots of unity, then I could use Kumar extensions and understand that these, in this tower, all the field extensions are, every block is Galva, and the group of automorphisms are cyclic. Okay, so what do I mean by that? By saying that if my base field had enough roots of unity. So I need n sub ith roots of unity for the ith step. I'm going to look at the least common multiple of n sub i's, or I'll be a bit more generous and let the product of n sub i's be n. And then I look at the nth root of unity, which means I'm going to split x to power n minus 1 dot n sub n minus 1. I'm going to split it over f. If this polynomial has distinct zeros over its splitting field, then I can add these zeros to f and then start looking at these n sub ith radicals and add them one after another to the new base field. Now, because my base field has enough roots of unity, all of these steps are going to be Kummer extensions, and we can get a better understanding of the whole extension. For this polynomial to have distinct zeros, we need to have that the derivative and this polynomial are co-prime and so on. And that's equivalent to saying that the characteristic of f should not divide any of these n sub i's. We can continue with this line of argument, and it's completely okay. But for simplicity, I'm going to assume that characteristic of my base field is actually 0. We could go ahead and just use this assumption that characteristic of f does not divide n sub i's. and the whole argument goes through. But again, as I have mentioned, I want to give you the main ideas. You can see that the whole proof goes through by the weaker assumption that either characteristic is 0 or it doesn't divide and sub-i's. Okay, but for now, let's assume the characteristic is f. Then automatically we know that every field extension that we are going to work with is separable. So then as soon as we get the normal condition, as soon as we get that certain field extensions are normal, we automatically get that extension is a Galva extension. Okay, so let's add the assumption that characteristic of the base field is 0. And let's add these enough roots of unity to the base field and call it E naught, which means E naught is a splitting field of x to power product of n sub i's minus 1 over f. Okay, so when I add this base field, let's see what happens. Let's observe this part of argument. Again, you've seen before, but it is crucial. I'm going to repeat it. X to the n minus 1 has distinct zeros in E sub 0 because it's a separable polynomial. I mean, not because it's separable, because characteristic is 0 here, I assumed. So therefore, it's all the polynomials are going to be. So if I look at the derivative of this polynomial, I get n times x to power n minus 1. And because characteristic is 0, it's going to be co-primed with x to the n minus 1. And therefore, it has distinct zeros. And it's a splitting field, which is E naught. Now let's A sub n be the set of zeros of this polynomial. This is E sub 0. So let A sub n be the set of zeros of this polynomial. But by what we discussed, this set has n elements. And what is clear is that if I take two zeros of this polynomial, multiply them, I get another 0 of this polynomial. Alternatively, I can think about this set of zeros as the kernel of the group homomorphism of raising every element to power n. Any method that you want. So there are at least two methods that I describe. We deduce that A sub n under multiplication is a group. It is a group of order n. Inside this group of order n, for every positive integer d that I give you, there are at most d elements of this group that satisfy the relation a to power d equals to 1. Essentially because every polynomial of degree d over a field has at most d zeros. So the polynomial x to the d minus 1 has at most d zeros inside the field E naught, and that means that inside A sub n, I have at most d elements that satisfy the equation a to power d equals to 1. From group theory, we know that if I give you a group with this property, if I give you a group G, and I tell you that inside this group, for every integer d, for every positive integer d, the number of elements inside the group that's raised to power d and ends up being 1 is at most d, then the group is cyclic. This we've seen before. Therefore, A sub n is a cyclic group, and it's generated by some element that we denote by zeta. So it is zeta, zeta is squared, and so on. And because it has n elements, the multiplicative order of zeta is precisely n. Therefore, zeta to power i's are zeros of x to the n minus 1, are distinct zeros of x to the n minus 1. But again, now I can use generalized factor theorem and compare the degrees and the leading coefficients and end up getting that x to the n minus 1 is x minus 1 times x minus 2 times x minus zeta to power n minus 1. that means, in particular, that means that E sub 0 is nothing but F joined with zeta. We've seen that such an extension, so now this argument that we have provided shows that this extension over F is a Galva extension, and the automorphisms of E naught over F is going to be a subgroup, can be embedded into Z sub n cross, the multiplicative group of Z mod n. I'm going to repeat this part of our argument as well because it's important. But let's connect it with the solvable, with polynomial f being solvable at the same time. So when we said that f is solvable by radicals, we meant that we have these extensions, and the only reason that we consider these nth roots of unity was because we wanted to work with Kummer extensions as the building blocks. So let's do that. Let's see how we can use this zeta and add it to f sub i's to get Kummer extensions. That's rather easy. We take the zeta and add it to E sub I. So what does this mean? That means that I'm thinking about, so this means that I'm taking the splitting field of x to power n minus 1, not only over f, but over f sub i's. I'm taking the splitting field of x to the n minus 1 over E sub m. And then I argue, as we did before, get a zeta, and then add that guy to f's. So again, what we are doing is like this. So I'm considering E sub m to be the splitting field of x to the n minus 1 over f sub m. By that, the top argument, we deduce that there exists zeta inside E sub m such that E sub m is f sub m joined with zeta, and zeta, the multiplicative order of zeta is n. Now I'm adding this zeta to E sub i's, to f sub i's, in order to create E sub i's. So the way that I wrote it, I started with the bottom. That's not the right approach. I have to start with the top one in order to make sure that it belongs to the largest field. Now I can add this larger element to the smaller subfields and create a subfield out of that. Otherwise, this notation over here doesn't quite make sense. So that's how we actually do it. I will repeat this part of the argument in the previous lecture. Here I'm just giving you all the needed steps and the blocks of this chain of radical extensions. So in the next time, we'll go back to this part of the argument as well. Okay, so I have these E sub i's, and now except the first part, except E sub 0 over f, the rest of the blocks are going to be Kummer extensions, and therefore the rest of the blocks are Galva, and the rest of the blocks have cyclic group of automorphisms. The first one, E sub 0 over f, is still a finite Galva extension, as it is a splitting field of x to the n minus 1 over f, and x to the n minus 1. And this splitting field is separable automatically because the characteristic is 0, or alternatively, we can say that the way that we chose the characteristic, if it doesn't divide n, it's going to have distinct zeros and so on. Either way, E sub 0 over f is also a Galois extension, a finite Galois extension. And let's repeat the argument that the group of automorphisms of E naught over F is a subgroup of Z sub n cross. How does the proof go? So if F is a field and the characteristic of F doesn't divide n, it's either 0 or it doesn't divide n, a prime number that doesn't divide n. E is a splitting field of x to the n minus 1 over F. Then the set of all the elements of E that satisfy this equation that alpha to the n is 1 is a cyclic group of order n. This part we have already argued using a result from group theory. This is a cyclic group of order n. And if I start with an automorphism of this field extension and restrict it to this group, so here I'm talking about group automorphisms, then this restriction is a well-defined function, is a well-defined injective group homomorphism. C sub n is a cyclic group of order n, and therefore the group of automorphisms of C sub n is isomorphic to the multiplicative group of Z sub n. This you've seen again before. When I give you a cyclic group, you look at the generator of the cyclic group, and every automorphism of the cyclic group sends this generator to another generator. So that means the power of it sends to some power of this generator where the power is co-prime to n. So from there we get an isomorphism between automorphisms of C sub n and the multiplicative group of Z sub n. So R gives me an injection of automorphisms of the field extension E over F to this group of automorphisms of Z sub n, and that is the multiplicative group of Z sub n. So this is in particular an abelian group. It's a subgroup of Z sub n cross, and therefore it's abelian. Okay, let's go over the proof. We have already proved the first part, that C sub n is a group, is a cyclic group, and it does have n elements. If I list elements of C sub n and call them 1, zeta, zeta squared, and so on, then E is generated by F and zeta. Because E is the splitting field of this binomial, it's enough to add zeta, then automatically we get the rest of the zeros. That means that every theta that I give you is uniquely determined by its value at zeta. In particular, it's uniquely determined as soon as I restrict theta to C sub n, because C sub n does contain zeta. If I tell you what theta is restricted to C sub n, I know what theta of zeta is. So I uniquely understand theta. I understand what theta is. That means R is injective. And let's also observe that every automorphism of this field extension permutes zeros of the polynomial x to the n minus 1. And that means that it sends C sub n to itself. So it's a well-defined map. So here again, I should have mentioned this. So let's write it over here. That every automorphism, so theta, permutes zeros of x to the n minus 1. And that means that theta sends C sub n to itself. So it is a well-defined, restriction is indeed a well-defined function. And clearly, restriction of composite group homomorphisms is the composite of restriction of automorphisms of this field composite of restriction of composite of two automorphisms of this field extensions is the composite of the restrictions. And that means that the restriction map is indeed a group homomorphism. So it's a group homomorphism, it is injective, and therefore we get the claim. And because the automorphisms of the group, the cyclic group Z sub n is isomorphic to Z sub n cross, that completes the proof. In particular, the automorphisms of E over F is an abelian group. That's an important part that we are going to use. Altogether, we showed this, that if F is a field of characteristic 0, if a polynomial small f is solvable by radicals, then I can find a chain of fields such that the first one over f comes from adding an element that's the nth root of unity, and the other ones, each one is coming from adding some n sub ith root of an element inside smaller field E sub I. So E sub I plus 1 over E sub I is a Kummer extension, and E sub 0 over F is an extension that comes from adding an nth root of unity to the base field. In particular, the first one, I mean, all of them are finite Galva extensions. And the automorphisms of the first one is abelian, and automorphisms of the other ones are cyclic. And what's the connection between this and the polynomial f? There is an intermediate subfield of this field extension, E over m, E sub m over f, which is a splitting field of the polynomial f over the field capital F. So we'll continue on this. Our goal is to connect these automorphisms of the building blocks with the automorphism of the entire E sub m over f. So we want to connect it with the automorphisms of E sub m over f, but we can do so only when E sub m over f is a Galois extension or is a normal extension. Here is characteristic 0, so automatically we get it is Galois. So we need to this for this guy to be Galois. So that is what we are going to do next. We are going to create a mechanism and change our initial radical extension to a Galois radical extension. And then we are going to add the needed roots of unity to the base field. So that's the order that we are going to take. So we start with a chain of f sub i's, where the last one, therefore the last one would be a radical extension. So I start with a radical extension of the base field f that contains all the zeros of the polynomial f. I change this radical extension to a Galois radical extension. So I need to argue why I can do that. So after changing it to a Galois radical extension, I add enough units to the base field. And I'll do it in a way that still I get a Galois extension. Then we end up getting the same chain as in this lemma with this extra property that E sub m over f is Galois. As soon as we get that, we can understand a very nice property of the group of automorphisms of L over f. You see, E sub m's are not canonical, but the ring L is a splitting field of the polynomial f. It's completely determined by the polynomial f. So we use these auxiliary fields to get a property of this field extension, or L over f. So we get a property for this group, which is going to be fairly special. Okay, we'll continue in the next lecture.